Hello, class. Just waiting for a couple of more viewers to show up, and I'm making myself some food because I'm starving, so I'll be right back. Okay. There are the viewers. Okay. I got myself a steamed bun with taro root in it. So, hot. Okay. Let's go ahead and get started. So, last time we learned about how to deal with diagonal forces. So if you have a force that is diagonal, like that, okay, then, so let's say it has a size f, and let's say it makes an angle, some angle with the horizontal, say theta. A diagonal force is equivalent to a vertical force and a horizontal force acting simultaneously, okay? And so you would use trigonometry to get the vertical and horizontal parts. So this would be f sine of theta because it's opposite the angle. And this would be f cosine of theta. Okay? We learned about applying Newton's second law when something is moving two-dimensionally. And so Newton's second law says that the net force equals ma. And when you have something moving two-dimensionally, Newton's second law applies both horizontally. So the net force in the x direction equals mass times the x acceleration. And then the net force in the y direction equals mass times the acceleration in the y direction. Okay? So what does that mean to say that the net force in the x direction? Well, the net force in the x direction is simply the rightward forces minus the leftward forces. Okay? The net force in the y direction is upward forces minus downward forces. Okay? So let's just do a little example just to make sure you understand it. What if I have an upward force of 100 newtons and I have a downward force of 50 newtons and a downward force of 30 newtons? Okay? And then I have a rightward force of, let's say, 60 newtons and a rightward force of 100 newtons and a leftward force of 40 newtons and another leftward force of size F. So this is just an unspecified applied force. So in that case, the net force in the y direction would equal up forces minus down forces. So 100 newtons going up and 50 and 30 going down. So 100 minus 50 minus 30 equals 20 newtons. And then the net force in the x direction is going to be equal to, let me take a bite here. Net force in the x direction is going to be equal to right forces minus left forces. So 100 plus 60 minus 40. And if we have a force that is unknown, we still have to include it in the net force, just as a variable. So minus F. So the most we could simplify that would be to 120 minus F. Okay? So there you have it. Today's lesson has no new content. It is just going to be more problems of the same type because I think that they're difficult, and so I want to make sure that everyone understands them. Okay? So for the first problem, all right, let's consider an inclined plane. So this would be like the skier problem, but let's have friction. An inclined plane with friction. Okay, so let's go ahead and draw the incline. It's a 60-degree incline, so quite steep. There is a 2-kilogram block that is at the top of the incline. There is a coefficient of kinetic friction equal to 0.2. Okay? And so the block is going to slide down the incline. And what we would like to know is what is the acceleration of the block down the incline. Okay? So, what we want to do first is we want to draw a free body diagram. So a free body diagram is a drawing like this, where we represent the object as a dot, and we draw the forces acting on the object. So we have the weight force points straight down, 20 newtons. Weight force is mg, 2 kilograms times 10 meters per second squared is 20. The normal force does not point upward in this case. The normal force points perpendicular to the surface. Because the surface is slanted, the normal force is also going to be slanted. So it's going to be perpendicular to the incline. So there's the normal force right there. And then we're also going to have kinetic friction. So how does kinetic friction point? Kinetic friction point is an oppositional force. So if this block is sliding down the incline, okay, kinetic friction is going to point up the incline. All right. So what we're going to do is we're going to end up rotating the piece of paper so that the incline is now flat. Now, what is the advantage of that? Well, if we look at the problem as it stands from this perspective, a lot of times in physics, if you change your perspective, the problem gets easier, okay? So let's imagine viewing the problem from this perspective. In this perspective, we have two diagonal forces. So we're going to have to use trigonometry twice to put these diagonal forces into a vertical and a horizontal force. Okay. Gravity is vertical, so we don't have to simplify that one. Okay. So we have two diagonal forces. If we rotate the paper and view it from this perspective, now normal force is vertical, friction is horizontal, and it's gravity that is diagonal. So what we've done essentially is we've exchanged two diagonal forces and we've turned it into one diagonal force. So we're only going to have to do trig with gravity in this case. So that's a simplification. Another complication with viewing the problem this way is that here the block is accelerating diagonally. So it has a y acceleration and an x acceleration. It's accelerating diagonally. If we rotate the piece of paper, okay, now it's moving horizontally, so it only has an x acceleration. So you see how in an inclined plane, we want to rotate our piece of paper in order to simplify the problem. Okay, it's from that perspective, it's much simpler. So, because this is a 60-degree incline, the amount that I'm rotating the paper is 60 degrees. So each of these arrows gets rotated by 60 degrees. Gets rotated by 60 degrees clockwise. Okay? So, when I get the components, these are called the components, the vertical and horizontal components of the weight force, I know that this angle right here is 60 degrees because I had to rotate the paper 60 degrees to make the incline flat now. Okay? So once I know that angle, I can use trigonometry to get the components. So this component right here is going to be 20 cosine of 60 because it's adjacent to the angle. All right, 10 newtons. I knew that, I just was not thinking. I was just mindlessly typing into the calculator. This component is opposite the angle, and so it's going to be sine of 60. Which is 17.3. So now what we're going to do is we are going to redraw the free body diagram with all of the forces being either vertical or horizontal. Okay, so I redraw it. Normal force is going up. Kinetic friction is going to the right. The diagonal gravity force is now going to be two forces, where this force is 10 newtons, okay, and this force is 17.3 newtons. All right? So, and these are so good. Who can write? So we're going to do Newton's second law in the y direction. There's a very good question in the chat. What happened to the 20 Newton force? So when we go from a diagonal force to a vertical and horizontal force, the original force goes away. So this diagonal force is completely equivalent to a vertical and a horizontal. So we replace the diagonal force with a vertical and a horizontal. Okay? All right. Who can give me an expression for the net force in the y direction? based on this free body diagram, there's a net force in the y direction. Who can type it into the chat? While I wait, I'm going to chew my bean bun, or my taro bun. Now, in this problem, the y component of the acceleration is actually 0. Okay? So the reason that the y acceleration is 0 is because from this perspective, the block is moving side to side. It's not moving up and down. Okay? So whatever your expression for the net force in the y direction, which no one seems to want to type in, it's going to be set equal to 0. Come on, someone type it in. Do it. I'm waiting. Yes. The correct answer is, so net force in the y direction is up forces minus down forces. So your up force is normal, and your down force is 10 newtons. Okay? So this is kind of similar to this example right here, where one of the forces was a variable. Okay? So now what I can do is I can add 10 to both sides, and I know that the normal force is 10 newtons. Isn't that nice? Okay, so type it into the chat if you know the answer. What force can you calculate once you know the normal force? So there's a special force that you can't calculate it unless you know the normal force ahead of time. Okay, so type it into the chat if you know. And while I wait, I will explain why the acceleration in the y direction is 0. So in my rotated coordinate system, the y direction is this direction. So the block isn't accelerating away from the incline or accelerating into the incline. So that means that its acceleration in the y direction has to be 0. It's accelerating along the incline, parallel to the incline, which is the x direction. Very good. So many of you have typed into the chat that this is going to allow us to calculate kinetic friction. So the formula for kinetic friction is mu sub k times normal. All right? Coefficient of kinetic friction is a given. It's 0.2. Okay. The normal force is 10. So that tells us that friction is 2 newtons. So this is 2 newtons. Now we go to Newton's second law in the x direction. So the net force in the x direction is m times a sub x. Who can give me an expression for the net force in the x direction? Type it into the chat if you know, based on this free body diagram. Whatever expression you get, it's going to be equal to 2a. All right. There's a question, where does the 0.2 come from? The 0.2 is the coefficient of friction between the block and the incline. And so it's just a given number. The only way to really get the coefficient of friction is to calculate it. So remember, so there are two answers in the chat. one of them is right forces minus left forces, and the other one is left forces minus right forces. So we're gonna, in this class, we're gonna take rightward to be positive. So the net force in the x direction is actually going to be 2 minus 17.3. Okay. So minus 15.3 is the net force in the x direction. Divided by 2. Negative 7.7 meters per second squared is the acceleration. So that's our answer to the problem. Okay? We're going to do another example that's very closely related to this first example. So what if we have the same block on the same incline? Okay? Still 60 degrees. Coefficient of kinetic friction is still 0.2. Okay? But now the block starts at the bottom of the incline and it's being kicked. It's been kicked. So it is sliding up the incline. It has an initial speed of 5 meters per second. So the block starts out headed up the incline. It's going to slide, and eventually it's going to come to a stop. It's going to reach its highest point. Okay? And so the question is, how far up the incline is it going to slide? Okay? So we will start off with our free body diagram. Our free body diagram has normal force perpendicular to the incline. Okay. We've got the 20 Newton weight force going straight down. Okay. Now, what's going to be different in this case? It's very similar to the previous problem, but there's one slight difference in our free body diagram. Yes, very good. So friction is pointing in the opposite directions. Friction is an oppositional force. It resists the motion. So if you're sliding up the incline, friction is now down the incline. Okay? So I'm going to rotate my paper again so that now it's like this. Okay? And I've rotated the weight force again by 60 degrees. Okay? And so I'm going to redraw my free body diagram, and I'm going to reuse all of the math that I did. So this 20 Newton force is equivalent to 10 newtons down, and then 17.3 newtons across. But then we also have friction going this way. All right. So everything works out the same pretty much because the normal force is still going to be 10 newtons because the up forces have to equal the down forces if the block is not jumping off the incline. And therefore friction has the same value. So this is 2 newtons. So basically the only difference is that friction is now flipped directions. So what does that mean about our net force in the x direction? Who can tell me the net force in the x direction in this case? Type it in the chat if you know. And then MA is going to be 2A. Yeah, so it's going to be minus 2 minus 17.3. So negative 19.3 equals 2a. So this is kind of interesting. If you have a block that's sliding down the incline, it actually has a different acceleration from a block that's sliding up the incline because of the friction changing directions changes the net force. Dividing both sides by 2 is going to give us about 9.7, negative 9.7 meters per second squared is the acceleration. Okay? So, we're trying to solve for delta x. So, rotating my piece of paper back. We are trying to solve for delta x. So, delta x is a question mark. The acceleration is negative 9.7 meters per second squared. The block is we want to know how far does it go up to its highest point. So just like with kinematics problems, at the highest point, the velocity is 0. So we know the final velocity is 0. And we know that the initial velocity from the kick was 5 meters per second. So now this has become a kinematics problem. Who can tell me which kinematics equation to use? All right. And while I'm waiting for someone to type it in, I'm going to take this opportunity to tell you that it is an incredibly good idea to have a blank piece of paper. For this class, it's an incredibly good idea to have a blank piece of paper and to write down all of the useful equations on that piece of paper so that you always have this list, this growing list of equations that are relevant, okay? And what that's going to allow you to do is to very quickly locate equations. You don't have to flip through your notes. If you need to flip through your notes, that should be to study how a problem is solved. But it's good to just have a reference sheet of equations. With Newton's second law, Newton's third law, the kinematics equations, the projectile motion equations, all the different forces equations, all that stuff. Excellent. So it's going to be the third equation, which says V final squared equals V initial squared plus 2a delta x. So V final is 0, so the left-hand side is 0. V initial squared is 5 squared, which is 25. 2a is going to be 19.3. I just know that because I multiplied by 2a here, and I know that that's equal to 19.3. And then delta x. So we add 19.3 delta x to both sides, and we get that delta x equals about 1.3 meters. So it's going to slide up the incline 1.3 meters and then come to a stop. All right? We're going to do 2 more problems. The first problem I want to consider is a wall. Okay? Suppose we have a wall this time. The wall is smooth, aka frictionless. Sometimes in a physics exam or something, you might hear the word smooth, which is code for frictionless. Okay. And there is a 3 kilogram block on the wall. And the block is being pushed by a force pushed, so it's pinned against the wall by this force, okay? And let's say that it is a 40 Newton force, and that this angle right here with the horizontal is 50 degrees, okay? And so what we want to know is, what is the acceleration of the block? All right? So I want you to think about and type it into the chat if you know the answer. What is going to be different about Newton's second law this time? There's something going on the right-hand side that's different from what we did last time. Okay? Think about how something that's stuck against a wall is going to move compared to something that is moving along the floor. All right. So I will draw my free body diagram. We have a normal force which points away from the wall. So the normal force actually points to the left because that would be the direction perpendicular to the wall and away from the wall. We've got this diagonal force of 40 newtons at an angle of 50 degrees. So generally speaking, with free body diagrams, we always draw the arrows as going away from the dot. So even though in the picture here I have the arrow going into the box, I'm going to shift it so it's going away from the box. And then I have a weight force, which is 30 newtons downward. Okay? M times G, 3 times 10. So I take this 40 Newton force and I break it up into components. So this would be 40 sine of 50, 30.6 newtons. This would be 40 cosine of 50, 25.7 newtons. So I can redraw my diagram so that all the forces are either vertical or horizontal. Okay, so I'm going to write this diagonal force as 30.6 newtons across and 25.7 newtons down. Do you guys understand why it's not a sideways and an upward force, it's a sideways and a downward force? Because this is a force that's angled downward. So the vertical part has to go downward. Then we also have the 30 newtons and the normal force going this way. So yeah, the idea behind this problem is that because it's on a wall, it's pinned to the wall, so it's not going to move left or right, but it is going to move up and down. So the y acceleration is not 0 in this problem, and the x acceleration is 0. All right? So because, so in this problem, a sub x is equal to 0. Okay? Because the block is moving vertically along the wall. So anytime you have the acceleration is 0 in the x direction, that means that the left forces have to balance out the right forces. Okay? If the left doesn't balance the right, then there's going to be more force to one side or the other, and it's going to accelerate sideways. Okay? So we can immediately say that these two forces are equal and that the normal force is 30.6 newtons. Okay. Oops, I made a mistake. Thank you for catching that. I goofed. This should be 25.7. I reversed my two forces. and this should be 30.6. Okay, so that was wrong, and this should be 25.7 newtons. I'm sorry about that. I goofed. Good catch. So now that we have this correct free body diagram, who could tell me an expression for the net force in the y direction? I'll write this as 3a. Waiting for an expression for the net force in the y direction. Minus 30 minus 30.6, yep. Because there's two downward forces, so they're both negative. So that means that minus 60.6 equals 3a, which says that the acceleration is minus 20.2 meters per second squared. Okay? So that's going to be our acceleration in this case. One of the things that's interesting about this is that the block is going to accelerate downward faster than gravity alone could accelerate it, because you have this additional applied force that is angled downward. It's basically adding on to gravity and pushing the block down even at an even greater acceleration than it would normally experience due to gravity. Okay? So we're going to do one more example today, and this one's a little bit tricky. And it actually has applications to, believe it or not, it has applications to fighting someone, okay? So let's suppose you have a flat surface, okay? And you have a block, and let's say the block has a mass of 20 kilograms. The block is not moving. So there's a coefficient of static friction equal to 0.8. Okay? There's an applied force, and it has an unknown magnitude. So I'm going to call it F sub A for applied force. And it makes an angle of 30 degrees with the horizontal, okay? And so the question is, the applied force must be greater than what in order to make the block budge? Okay? So how big does the applied force have to be in order to make this block start to move? Okay? So we're going to do this exactly like we did before, okay? But the variables are different here. So doing a free body diagram, we have this applied force at an angle of 30 degrees. We have the normal force going upward. We have the weight force going down. The weight force, because it's a 20 kilogram block, is going to be 200 newtons. And then because this force is generally pulling to the right, static friction is going to point to the left. Okay? So now I want to redraw my free body diagram, this time with all the forces being vertical or horizontal. So this is where it's kind of tricky, okay? This would be F sub A sine of theta. So sine of 30. But we don't know what F sub A is. However, we do know that sine of 30 is 0.5. So whatever the value of f sub a is, we know that this vertical component is going to be 0.5 f sub a. Okay? So the component is unknown. It's an unknown variable. All right? The horizontal component is adjacent to the angle, so it would be f sub a cosine of 30 degrees. And I know that cosine of 30 is 0.87. See that? So whatever the value of f sub a is, the horizontal component is going to be 0.87 f sub a. So when I redraw the free body diagram, it's going to be like this. I've got the diagonal applied force is going to become a horizontal force of size 0.87 f sub a and a vertical force of size 0.5 f sub a. So that's what happened to the diagonal force. Then we have normal force. And we have weight force. I think my pen might be dying. You're witnessing the moment of death of my pen. You've witnessed the moment of death. I have a new pen. Like that, okay? Let me make these a little bit darker. Okay, so in this case, the block, once it budges, it's going to be moving horizontally. Okay, so we have that a sub y equals 0 because it's not going to slide. Once it starts to move, it's not going to slide vertically, it's going to slide horizontally. So the net force in the y direction is equal to 0 because that would be the right-hand side of Newton's second law. So type it into the live chat if you know an expression for the net force in the y direction based on this free body diagram. Yes. Okay, very good. So the up forces are normal force and the 0.5 applied force. The downward force is 200. And so that equals 0. So now we have that the normal force is equal to 200 minus 0.5 f sub a. Now this is kind of interesting because you can see that the bigger the applied force is, the smaller the normal force is. So by pulling up, you actually reduce the normal force. Okay? Now that in turn is going to allow us to calculate the maximum static friction. Okay? So maximum static friction is mu sub s times normal, which is going to be, the coefficient of static friction was 0.8. It's right here. So 0.8 times 200 minus 0.5 f sub a. And that's equal to, I'm going to distribute the 0.8 to both terms. So I have 160 minus 0.4 f sub a. All right? So I know what the maximum static friction is. Now here's the thing. The horizontal applied force must be greater than the maximum static friction to budge. You have to overcome friction in order to make it to budge. Okay? So what is the horizontal applied force? It's 0.87 F sub A. So we must have 0.87 F sub A has to be greater than 160 minus 0.4 F sub A. You've got to have that inequality as true in order for it to budge. Otherwise, friction is stronger than your horizontal applied force. Okay. So adding this over to the other side is going to give me 1.27 F sub A has to be greater than 160. Dividing both sides by 1.27 gives us 126 newtons. The applied force has to be at least 126 newtons in order to budge. Okay? Now, why is that interesting? Well, I'm going to do a little aside here. What if instead we had applied the force horizontally? What if this was F sub A? What if the force was not angled? It was instead just purely horizontal. If you did the problem this way, you would find that the applied force, so if you applied the force horizontally instead of at a 30-degree angle, you would find that the applied force would have to be greater than 160 newtons. Okay? So the lesson is we reduce the necessary applied force to make something move by pulling at an angle. And the reason that we do that is because pulling at an angle makes the normal force smaller, which reduces friction. Okay? So what does this have to do with fighting someone? If you're fighting someone and you're trying to push them back away from you, you should not push directly. Because if you push directly, you're going to have to apply a greater force to make them slide backwards. Okay? You actually want to get underneath them and push up at an angle, which will reduce the normal force, which will make the maximum static friction smaller, so they have less traction and they go back more easily. So you can push them back more easily if you push them up at an angle. Furthermore, if you're pushing them up, then according to Newton's third law, they are going to be pushing you down into the ground. And if you're getting pushed down into the ground, then your normal force is increasing, which increases your friction. So by pushing someone up, you're making their static friction less. They have less traction, and you're making your own traction greater. Okay, so that's going to put you at an advantage. So anyways, so that would be my lesson to you. If you get into a fight, get underneath and push up if you want to make them slide away from you. Okay, so that's my lesson for today, and I will see you in the Zoom room.